So again, it's great to have you here, Alan. Thanks a lot for taking the time to join and share kind of like your experience doing authorization at Airbnb. But before we get started, what I usually ask people is like, tell us a bit about what you do at Airbnb, kind of like what your role is, what your team does, to kind of like share some context.
Yeah, thanks for having me. Yeah, I've been working at Airbnb for about 5 years now, working across basically the user authentication and authorization stacks. I've worked on everything. Started with preventing ATOs, then moved to building the authorization infrastructure, which is Himeji, based off Zanzibar. I also work a little bit on user authentication. Yeah, just a software engineer.
Good. That's great to hear that. And then again, you're definitely kind of like a person with expertise in the space. For anyone listening, ATOs are account takeover attacks.
Yeah.
So why are we chatting? Why are authorization? Why is authorization? Why are permissions important for the Airbnb from like a business perspective?
Yeah, it comes down to basically the need to expand the business model from just a single guest and a single host making reservations with each other. As the business needs to introduce more concepts that require authorization, for example, co-hosting, teams, co-traveling, business travel, and so on. All of this introduces more users into the fray of who is allowed to view what sensitive data about a trip, about a listing, about another user, and building out that authorization model at scale correctly. That introduced a lot of complexity and made authorization really a core part of our tech stack very quickly.
Okay, it's very interesting. So this was kind of like not a feature that Airbnb, the product, the company, started with, but more something that you grew towards. Can you give us an example of like how authorization works with like co-hosting or teams or business travel? Like maybe one of those so that people can understand, oh, this is where authorization is happening.
Yeah, so traditionally, when you go on Airbnb as a guest, you're going to book a listing that gives you a reservation that creates a trip that you're going to travel on. You get to know the listing details over time as you get closer to check-in. And you got to interact with the host. The host is going to send you messages. They'll expose some information to you. You get to know more about the host once your reservation is confirmed. Once there's more than one host in the picture, there's a lot more product complexity and policy and authorization decisions to be made. For example, a co-host might need to do everything that a host can do. They need to interact with guests. They need to update the listing information, send, the Wi-Fi details over, and all of that. The co-host needs to see all the listings that they're managing, aside from as opposed to just like a host who creates and manages listing. A co-host can manage things for many different hosts. And all of this like many-to-many authorization entity-to-entity authorization model just leads to it being a core concern for Airbnb, where it has to work correctly, otherwise the product doesn't work, and it has to work quickly, otherwise the product is slow.
Okay, that makes sense. So kind of like these more kind of like collaboration economy scenarios brought the need for collaboration like features within the product, and then that's where like authorization at this kind of like scale starts to kind of like become a pain potentially, right? Because you have lots of co-hosts, lots of listings, lots of ways in which those can be related, and kind of like you seem to hint that it's not just about can we get this right, but can we get this done right fast, because that probably impacts your bottom line.
Right. And if we don't do it efficiently either, like say we're just generating a lot of load on our databases and systems, that generates real life just compute costs and all of that as well.
Yeah, that makes sense. So you mentioned kind of like the rise of complexity in an original implementation, and I know kind of like back in April, you and the team wrote a blog post sharing how you kind of like revamped the permission system. What issues did you have kind of like before implementing this new permission system?
Yeah. Yeah, we're basically coming from a world where the permission system had been built bit by bit over time. As each new product arrived, everyone just tried to figure out how to best add it to the existing permissions checks that were just scattered across at the API layer and across services and so on. The issue is we basically saw a situation where the the velocity at which these new business needs came up was really greatly exceeding the ability of everyone to make these changes. Once the overall engineering systems become complex enough, uh, when a business need comes up, like we got to enable this new feature that involves authorization. The team that has to implement the feature has to go and look at every single place where a permissions check could be happening and update it. And that just quickly became non-scalable, as this is not just limited to like collaborative features, but as we start imposing like policies, like when listings get restricted or so on, um, all of these new ideas that require authorization just kind of run into just the engineering effort brick wall.
Yeah, that makes sense. Seems that like as like the system organically grew and complexity also grew with it, it was hard for engineering and product teams to make changes because of that complexity, and it probably was easy to make mistakes. Small changes probably required making numerous changes across the product, and kind of like you were hitting all of these bumps from that organic growth. Is that an accurate depiction?
Yeah, that's pretty much exactly what happened.
Yeah. So I guess kind of like improving that engineering and product velocity was a goal with this new implementation. What other goals did you have with kind of like this new system, Himeji, that you built? How did you start thinking about those?
I think the other really big goal that we were targeting was just to tighten up data security. It's like a huge topic and it's growing more and more every year as we see more companies having data breaches and facing the consequences of them. Um, we just saw that every new product that came out had to go through a rather um, difficult and lengthy security review process for us to make sure that the data was safe and it wasn't being improperly exposed. And that audit gets tricky to do at scale without data security being implicitly designed into the way the entire system works. There's a lot of consequences for data breaches nowadays, and we wanted to just really lock down and make sure that it's really easy for everyone to do the secure thing and also make the product as correct as possible all the time and just minimize the amount of defects and poor user experiences that happen when permissions are inconsistent.
Yeah, that makes sense. So there's an aspect there of like again making things easier internally for a lot of other engineering teams across the company. That's kind of like more a platform-like vision for what you build, right? It's not that you're building something for your own team's use. You're building something for other engineers to use.
Exactly. And that's how we envisioned Himeji to be used and how it is used today. It's effectively primarily a platform.
Good. So what other options did you explore before kind of like the one you landed on with the Zanzibar-based approach? What did you research and what made you go with Zanzibar-like approach over other things?
Yeah. We had a relatively long phase over the course of, I would say, maybe like a year or two of just exploring other approaches and trying to build other systems around, say, like groups and role-based access control. And we came to the conclusion that basically you need relationship-based entity-to-entity authorization. And kind of the more primitive forms of roles and just like ad hoc permissions written into tables on models and just trying to like glue that all together. While it's incrementally less work in like the short term, we realized it just wasn't tenable in the long term. So we tried out a lot of things related to just trying to like build authorization services that weren't necessarily like a full Zanzibar. And we realized that, you kind of just have to commit all the way and basically build the whole Zanzibar system to really make something sustainable in the long term.
Okay, so this is kind of like where we're starting to get into the meat of this. We're talking about Zanzibar. Can you briefly describe what you mean by that? And again, I'm familiar with that because we're building it as a SaaS. It's been built by you, but by Carta. There are other companies building this as a SaaS. There are open source implementations of this. But for anyone that hasn't heard of it, how would you describe Zanzibar and the Google Zanzibar model?
It's a really interesting question. Really, for us, Zanzibar is about the flexibility of combining a few things. The first is to model permissions based on relationships. The second is to configure permissions based on like a flexible algebra, as opposed to code and as opposed to just like relying on the relationships for everything. And the third is to centralize everything as in one place, with the main motivator for that being consistency and speed. Zanzibar is so incredibly fast that you can have it at the data layer so that you can solve all your data security concerns by running your rules at the data layer. So you kind of have this like safe peace of mind that you're not going to mess up and like rely on upstream clients to behave perfectly correctly to protect your company from disaster.
Yeah, I like how you went through those because it's also kind of like how I usually kind of like explain Zanzibar, right? Instead of basing your authorization decision on a user's role or on the users and the object's attributes, what you do is you base them on the relations that they have. And you need to do those three things, right? You define your authorization model, meaning that it's flexible. At the same time, you use kind of like that set algebra for declarations, which prevents you from shooting yourself in the foot. And it has some very interesting kind of like reverse indexing grammar capability so that you can ask questions like what objects does a user have access to? And then, of course, the notions around the latency, right? If you do this right, if you implement the concepts from the paper, if you also limit the interface and the grammar, you get a very powerful, very fast implementation, which is kind of like what you were also looking for.
Yep, exactly.
So kind of like getting into the weeds, what's the architecture of the system? And you talk about this a bit on the blog post, but I would like for people to kind of like hear it and also start kind of like digging into the different components and what made you pick each of those.
Yeah, I think actually Zanzibar conceptually is pretty simple. It's the really core part of the architecture is a tuple store. For us, this is a database. For Google, that's Spanner. A cache, which is really critical to your ability to scale and make things fast. In Zanzibar's case, the really core component of this cache is that it's not like a look-aside cache. It's integrated into your read path. The cache itself should be responsible for both storing data and hydrating data in the case of misses to prevent stampeding herd problems. And then the third piece of architecture, just building from the ground up, is the servers themselves that have to take requests, interpret the request with the configuration to determine what data it needs to fetch and how to resolve it, and basically resolve the check to, using the configuration and the data fetched.
Okay, good. So we talked about like a couple of interesting components. We talked about, again, the database. We talked about the cache. The database stores tuples, and then we have the cache, and the cache kind of like reflects the queries that you perform against the system. It doesn't store the tuples itself, but it stores data about like, hey, does this user have access to this listing, or can this host perform this action on this chat? What were your technology decisions here? For example, you mentioned Google uses Spanner. What database did you pick? And what are the scaling characteristics? The same thing for the cache. What technology do you use for the cache?
Yeah, this is where we we had to do a little bit of exploration and try to figure out what would work best for us at on a cost effectiveness basis. So for the core tuple storage, we ended up using RDS. This is not the perfect solution. We'd obviously like Spanner, but it works because it's cost efficient for Airbnb, as opposed to something like Dynamo, just because of the way Airbnb's contracts and AWS architecture is set up. The downside of us picking RDS for our tuple storage, we just have to be really good about our cache hit rate, because RDS doesn't have the same level of horizontal scalability that Spanner does.
Yeah, that makes sense, and I kind of like I guess one of the reasons why, again, so Spanner has that ability to do sharded SQL queries, but at the same time, like get those like asset consistency across shards. That's not in any database out there. But I know you're also kind of like, you don't require that strong consistency everywhere from how you model things. But at the same time, you also hinted at Dynamo, and I guess this is my take. Maybe you can correct me if I'm wrong. But for anyone listening, that's probably kind of like an intuitive choice, given its like natural partitioning and horizontal scaling capabilities. Is that kind of like why you made that mention?
Yeah, Dynamo feels more. If you're looking at the AWS stack, I feel like most people would intuitively think that Dynamo is the right thing to do here. We didn't choose Dynamo for two reasons. The first is that we basically optimized our database to be super efficient in the tuple storage. Like just requesting a set of tuples that is typically going to be requested is just going to minimize the amount of pages that are loaded based on how we set up the index. And also for us, just on an AWS pricing basis, I'm not really privy to the details, but we calculated it out, and Dynamo would have just been so much more expensive on like a sheer dollars per tuple and QPS basis that it would just be much more feasible to use RDS.
Yeah, that makes sense. And one of the things that blew my mind back when we talked a few months ago was that, hey, we optimized things so far that the number of pages read whenever you read tuples is very important.
Yeah, exactly. You want to, minimize how often you actually need to go to disk, and you end up with a really high buffer pool hit rate. So you're effectively somehow managing to read mostly from memory and mostly just within a very small cluster when you do need to go to disk, so you don't end up seeking too much. And with all that optimization, we kind of found that we were in a pretty decent place with RDS, and we didn't have any scaling concerns on like a 5 to 7 year time horizon at the very least.
That's great, and it's great that you're kind of like thinking that far ahead. So let's kind of like take people through the journey, right? So a new host is added to co-host group or things like that. You might be writing tuples about that kind of like host group membership over to Postgres. So you have an API, you write that tuple. Then when you do a check, you call this like check API that the paper mentions to check, hey, can this user perform this action? We also mentioned the caches. What caches are you using, and how are those caches populated?
Yeah, one of the key things with the Zanzibar paper that it took a few really deep reads to realize was the importance of tiered caching. So we have, you can think of there being like three layers, right? The database, the caching layer, and then the orchestrating layer that receives the checks. The key thing here is that there's a cache directly above the database. So suppose I ask for all the tuples related to like listing 10. That cache is going to be able to do some filtering and have all that data in memory if it's a hit. And if like 10 services are requesting checks on listing 10, it can batch all of the loads into a single one to just minimize the amount of load we generate to our databases. And this aspect of protecting the databases from duplicate load ended up being super important for us as well. So that's like one of the really important caches, just right in front of the databases, reduces load, does preliminary filtering on the principals that are being checked and so on, just to minimize the amount of data being transferred up. And then even within the orchestrator, the service that's actually getting the check request, we have an additional layer of caching. We cache those kind of direct authorizations, like a service or a specific principal is authorized on certain entities, like kind of a derived concept based on the configuration, as well as some tuples that are super hot. Any tuples that are going to generate disproportionate load to the database are going to be also cached client side. So we end up having these like two layers of caches, just with the goal of making things faster and reducing the amount of load that we're sending to RDS, and just like optimizing the query patterns so that whatever load does go to the database, it's really efficient to serve.
That makes sense. So you mentioned a couple of things. On the one hand, you mentioned kind of like the orchestration layer that would be kind of like the service, right? So there's a service, the service sends a request to the cache. If it's not there, the request to the database kind of like goes through. When we talk about that layer, I guess for caching to be efficient, and again, this is also hinted at in the paper, you need some sort of session affinity, right? In the paper, it's with consistent hashing. How are you implementing that?
Yeah, exactly. That's something that you have to do. For us, we have some like 80 different cache shards, and each entity based on its ID is going to consistently hash to one of those shards. And all loads for that entity are just going to end up on the same set of replicas on a shard, just deterministically.
That makes sense.
Yeah.
Another thing that's kind of you mentioned was like you're caching some tuples. At what layer are you caching tuples? Because like, caching tuples at the orchestration layer is probably not something that happens, especially because the orchestration layer doesn't interpret those.
Actually, we have to cache tuples at both layers. And this is kind of lightly mentioned in the paper. I think they basically call this like hot keys or something like that, or some. It's basically to reduce the impact of a hot entity. So we noticed that some entities just get disproportionately more traffic. Like one specific entity ID might get, say, like 10,000 checks per second, and within the same entity, all the other ones get like 100 or one or less. And because of that, the cache shard that's responsible for that super hot entity ID is going to get completely overwhelmed compared to all the other shards. So we just do some detection of which of these entity IDs is super hot and cache that data on even the orchestration layer so that it doesn't even go to the cache shard. And the amount of those we can cache is very limited, so you basically have to just limit it to the ones that are super, super hot.
Okay, so in that case, what you're doing is you're caching the result of like the cache or the database read query, not necessarily the check, so that like you can pre-compute checks beforehand. So it's a mix
Yeah.
of like caching. Are you also doing prefetching in that case?
Yes. So where caching, this is kind of where the word caching almost gets overloaded because, yeah, what I just described is caching the result of the data space query, not the result of the check. But we also do some caching of the result of the check in certain cases. For example, just to match the business needs, like we can't make statements about this generically, but for example, we know that um, suppose say a certain principal type is granted access to a certain entity type, and uh, if it's revoked, it doesn't matter if it gets revoked now or in an hour. It just needs to get revoked within the day. That seems like then when we discover situations like that that are also high volume, we manage to cache the entire result of the check for some period of time.
That makes sense. That's good, and thanks for sharing. That's very interesting, and one of the things that we were starting to look at for kind of like our SaaS implementation, but still aren't doing today. Another interesting thing that the paper mentions is leopard and arbitrarily nested groups of objects, right? So there's complexity when there's lots of nesting because you have to go keep checking, hey, is the user in this group? And if the group has lots of groups, do you have those use cases at Airbnb?
Yes, we do have nested groups. And there are a few use cases where the group fan out is really horrendous. Like a user, like sometimes an entity will be part of like basically what is effectively like 1,000 groups, and then we have to go to every single cache shard and load, 10 over 10 groups from each cache shard, and then fan out from there again. And that's where Leopard really shines and becomes a necessity. What we found actually is really interesting, which is that in order to get Himeji off the ground, we didn't need Leopard for basically an entire year and a half. Only, at least for Airbnb's use case, the nesting was very concentrated, all in like basically one entity had really severe nesting. And it was one of the later ones that onboarded. So we didn't need to build it at first, and then we later encountered really severe nesting, and it became mandatory.
Okay, that makes sense. So that was kind of like a happy mistake or a thing that happened by chance due to kind of like the onboarding order. It wasn't anything that you planned for, right?
Yeah, we didn't initially know that it would be like that, but it just worked out.
Good. And when you do this, like again, the group unnesting, how are you doing that? Are you just unnesting what would be known as like user set membership, where like in the paper you would say, hey, this user belongs to this user set because like the relation, or are you denormalizing everything all the way to interpreting unions and intersections and user set rewrites from the namespace configuration? Which one are you doing?
It's just the first one. Once you throw in unions and intersections in the group traversal path, it gets exponentially more difficult to do the denormalization. And what we've actually found is that at least for our business use case, that doesn't really come up. So it's sufficient just to basically denormalize away like a single layer of user set memberships, or what we call references, basically.
Yeah, that makes sense. One of the benefits of doing that is that you don't have to re-index things whenever the authorization model changes, because that's kind of like the user set data is all part of the database, whereas the rewrites and the union, like the set operators, are all part of the authorization model, the namespaces configuration.
Yeah, that's what we found was just like if someone added something to a union, we'd have to completely re-index, and that would just be impractical.
Yeah. So how often does the authorization model change, and how do teams work on like making those changes in a kind of like reliable fashion?
Yeah. I think our authorization model changes maybe not that often. Sometimes once or twice a week, we will make tweaks to the authorization model, but this is something I believe we also observe from Google, which is that it doesn't, or like Zanzibar doesn't necessarily plan for you to change your authorization model like once an hour. Authorization model changes are relatively infrequent and are kind of expected to be rolled out cautiously. So when someone makes an authorization model change along with the necessary tests, we kind of do an incremental staged rollout. The new authorization model will run for, say, 1% of requests, then 10% of requests, and so on in a canary, and eventually, and just slowly ramp up while automatically just monitoring authorization and error and latency rates to make sure that it's basically happening safely and as expected.
So, and is this something that you handle kind of like in an internal proxy layer, or do you provide a mechanism for your internal clients to specify which version of the namespaces configurations / authorization model to use when they're making a change? Basically, like they go change an variable or something like that, and they start using a new one.
So clients don't actually specify which version they want when they call check, but instead developers can basically choose to say, like, it's almost like deploying a new schema version. They can say to basically start a deploy of a new authorization model, and it will run through this canary process automatically against all of Himeji.
Okay, and in those cases, naturally, all of the tuples remain the same. All that you're doing is you're changing how the quote orchestration layer, the stateless without considering the caches, handles those queries, right?
Exactly.
Yeah, that makes sense. Another big thing in the paper is the notion of a Zookie, and the importance of external consistency for Google and the new enemy problem. What are your takes, or at least what are Airbnb's takes on it, and what's your need for Zookies? There's no specific mention of how you use them on the blog post. We just kind of like what led me to that question.
We did basically an audit of all the production authorization models and how they are checked at the time of design. And we essentially found zero need for strong consistency aside from the concept of read after write. So we essentially decided to support only the read after write concept, where you can create an entity, create a tuple for an entity as that entity is being created or modified, and then come back and do a check against that newly created entity by declaring that you are in the same request path. But outside of that, we actually haven't had any need for strong external consistency. It's just really rare to have a business need for, say, granting or revoking someone's permission, and within like milliseconds, they're here trying to do exactly what you revoked them from. And even if they're able to do it, we haven't found really business needs where it's so sensitive that like the moment that the permission is meant to be revoked, if they're able to continue doing it for like a few seconds or a minute or so, that it's a concern.
Yeah, so that makes sense. One of the things, again, like we've also been thinking about and seeing is that what typically might happen, even in these kind of like multi-region environments, is that you might be changing a specific permission. So you might be kind of like writing some tuples, and you expect to be able to read them. That's kind of like that read your own rights type consistency. But by the time you let someone know that you made that change, or that they have that access, it takes a few minutes, a few hours, right? And again, you don't want replication lag to be at that level, but still, it's different than, hey, it needs to be instant. And the other thing, of course, is that like Zookies add complexity to clients, right? Clients have to manage them. Clients have to pick when to use them. Clients have to tie them back to their original model to know kind of like which Zookie to use for each object. And it's not trivial. It's very easy to make mistakes with that as well.
Yep. And our clients are really quite used to declaring that they're in a basically read after write kind of object creation. I'm about to read my own write flow. There's a lot of that in our reservation or listing or user creation flows. So it was natural to add, and we haven't observed any problems at all with it.
Yeah, that makes sense. One of the interesting things that you and I discussed a few months ago when we chatted was there's a couple of things that aren't in the paper but that are useful. And I think one of them was called virtual groups, if I remember correctly.
Yes.
Can you talk a bit about those?
Yeah. This is because Airbnb has a lot of kind of request contextual authorization that happens in a semi-secure manner.
What is request contextual for anyone that might be listening and not familiar with that term?
Yeah, that's basically the idea that your authorization depends on not just the relationships that you have in the data or something that's declared, but aspects of how you're making a request to Airbnb. Think where you're making a request from. Are you in the UK? Are you in China? Are you in the US? Things like, are you in an experiment treatment group? Is your language set to something? All of these kind of contextual things that can change on a per request basis sometimes work their way into the authorization model, sometimes because of policy. For example, start viewing a listing while in a certain locale or something like that. And that sometimes needs to be strongly enforced at the data layer. So virtual groups is a way to say, declare a group membership to say that a user is, say, part of the user is currently in the UK group. And that is set by determining based on the request metadata that the user is in the UK. And we treat that within Himeji as a tuple that is true and matches, almost as if we had fetched it from the database itself.
Okay, that makes sense. So let me kind of like try to put the full picture together, both for me and anyone that's listening. So let's say you have a requirement that is, hey, someone has permissions to view a listing unless they are in specific geographic regions, okay? Mm-hmm. So I guess at listing creation, the first thing you do is you need to kind of like create tuples to say who is excluded from what regions are excluded, right? Something like region is a namespace, and you need to say region ID or something like that. Mm-hmm. And then you define kind of like region membership, and you add that to an excluded viewer group. A relation to the, okay. And then you need to go to the namespace configuration, and you need to say, hey, there's a kind of like a set difference operator here, which is anyone that can do this, but is not in this excluded group. Is that kind of like the next thing that you might do?
Exactly.
Okay. And then the third thing you do is you send this check request, and in the check request, you send the tuple that says that the user is a member or is coming from that particular region. That's what the tuple says. So does that all tie together correctly?
Almost. I think the part at the end where you send the tuple that the user is in a particular region, the key thing there is that this is where it somewhat ties to authentication, is that the data that the information that a user is in a specific region needs to be authenticated. It needs to be signed by an authority that is trusted to the authorization system, so that no particular service can just improperly declare that they're in any random region. Aside from that, that's accurate.
Okay, so there's a trusted issuer or a set of trusted issuers that are kind of like Himeji trusts. And whenever that one of those signs a particular, I guess, kind of like credential or request payload, they can include these kind of like tuples in the request payload. So as long as you trust the issuer of the credential, you can go and like run the check like that. Is that accurate?
That's accurate. And in practice, there's slightly less secure ways you can do this. For example, you can just trust that your upstream is passing you the correct request metadata, and you could extract it yourself in Himeji and so on. And we have that as like some intermediate solutions for like policy rules that are not sensitive.
That makes sense. And then when you are using, like, how do you consider those tuples when making queries to the cache and to the database? Do you have like a layer that essentially kind of like takes the request payload and abstracts the notion of like the source, whether the tuples come from the payload or from the cache?
Essentially, when we're traversing the configuration, they're going to get resolved when you traverse the configuration without going to the cache or the database or anything. And yeah, it's essentially, normally there's an abstraction that says, hey, go get this from the database. And then next time you evaluate the configuration, if it's been properly fetched from the database, then we'll try to see if it resolves or not. For a virtual group, you can just resolve it right away based on the information passed to you in the request metadata.
Makes sense. Are there any other concepts that aren't in the paper, but you also added to your system because you thought they were useful or necessary?
I think there's several concepts maybe that might have been lightly touched on by the blog post. For example, one concept that we have is the disassembling of an entity, or I guess a Zanzibar namespace, into parts. And that's just for a logical grouping of fields, essentially. Like, a listing can be disassembled into its description, its location, its Wi-Fi info or whatnot. That's not something that's really in the Zanzibar paper, but something we found practical to implement to just make it easier to integrate with data services.
Okay, that makes sense. So you found or you implemented a way in which you sort of like logically group namespace configuration pieces into different hierarchies or composites. Is that kind of like how it works?
Exactly. And this is roughly because Airbnb doesn't have, like, it wouldn't make sense for Airbnb to have, like a listing description namespace and like a listing amenity namespace and like one namespace for each of these. As Airbnb tends to a model of having like very few namespaces, but a few like really, really big and complex namespaces.
Yeah, that makes sense. So that probably is useful for tooling, not just integration with other services.
Yeah, and we ultimately ended up investing a lot of time after initially building out like the core infrastructure into tooling. It's Zanzibar is actually a really complicated concept for just any product developer who has no prior experience working in authorization to wrap their head around and to work with. So we had to build a lot of tooling both around how data and tuples make their way into Himeji, and how to keep it consistent. The concept of a relationship being represented in someone else's database and having it in sync with Himeji, and also around how to visualize, debug, and query and control how a data service integrates with Himeji while just like maintaining reliability and observability. We had to build a lot of these toolings that weren't really mentioned in the Zanzibar paper just because of the nature of how our team is responsible for a little bit more to get the adoption we need.
Yeah, and that's something we've seen again talking to other companies that have built Zanzibar-like solutions. For example, some of the Carta folks mentioned the internal education aspect, but this goes beyond Zanzibar-like solutions and more towards any internal platform team building products for like internal products, but still products for other things, right? You want to do that, like make things simple and education and all of those things. Do you have any use cases for time-based permissions and time-based tuples?
We do, and this is actually something that we had gone a little bit back and forth on. It almost feels natural to try to provide the ability to manage when a tuple should be created or deleted based on time. Giving an expiration time or so on. What we found after looking at basically the first 3 use cases that were time-based is that there was so much business and product logic intertwined with the concept of when to create and when to expire a tuple that there is no kind of platform-like solution that we could provide. This is because, for example, if you think about the life cycle of a trip on Airbnb, someone makes a booking, has a check-in time, has a checkout time. There might be things that you want to reveal close to check-in, close to checkout, and maybe not after checkout or so on. Like if you define all these rules, but the check-in time and checkout time are mutable, all of a sudden, not only are you managing the time when you think a tuple should be created and deleted, you also have to manage the concept of when these times need to be changed, how to look up a scheduled creation and deletion, the product requirements for when a tuple should be created or deleted. And we realized we'd basically be completely re-implementing a complex scheduling system. So long story short, there is no concept of time in Himeji, and it actually simplifies the architecture and performance greatly.
That makes sense. Yeah, that's one of those things where like there might be simple cases, right, where you say, hey, I want this tuple to either start applying or stop applying at a time. Mm-hmm. But when you go towards like any of the edges, it gets more complex. And this is like any other trade-off, right? It probably adds complexity to the system, it adds to your surface, and it needs to provide a lot of value for teams in order to be worth baking into the core.
Yep, and we just never found any cases that were actually as dead simple as it seemed. And one theory that I have is that like that ultra simple case, if it really is that simple, it's also not that valuable for us to provide a system for managing it either, because it's already simple for them to deal with.
Yeah, that makes sense. Another kind of like big thing in the paper, and kind of like after this, we're going to talk a bit more about kind of like some of your Airbnb specific use cases, but it's a search use case, right? The paper mentions Leopard, and like you can use the Watch API to build your own indexes. The paper mentions that search use cases might result in a lot of checks while you're checking the search results. So this is when the challenge when you're trying to do something where you're trying to do a search over a set of entities, and this might be full text search, and you might need to do paging and sorting. How are you solving that at Airbnb?
This is one of the hardest problems for us to solve. And I say that because it's one of the core queries that is issued on a regular basis. If you're a host or a guest, you want to see the listings that you're responsible for, or the reservations that you're responsible for, the trips that you're going to go on. And all of these are implicitly permission-aware queries. Same for if you're searching for a new listing, you don't want to see a listing that you can't book. All of these are permission-aware queries, and there's no super easy solution to it. The only solution that we found and that we saw implemented based on Zanzibar is to effectively publish mutations for when permissions change. So our search index will have to listen and say to when a listing becomes visible or not visible to be searched for, or when someone gains the necessary access to manage a listing. That means one of our Elasticsearch clusters that's responsible for searching through the listings that you can manage is going to listen to that and update an internal index that kind of denormalizes out from your user ID to the listings that you are responsible for. So that's kind of how we've solved it, I guess. I don't know if it's really solved it, but basically we concluded that you have to publish mutations, index them into a secondary index like Elasticsearch or something like that, and denormalize it there and try to keep it up to date.
Yeah, that makes sense. And this is kind of like one of those things where what you're trying to do is you're trying to kind of like maximize the probability or increase the percentage of the total search results return that the user will actually have access to. You can always kind of like go check later, but like doing that iteration and like cursor paging, that's a complex thing, because what you're essentially doing, if we step back from Zanzibar, it's like this is a multiple service join together with search, pagination, etc. This is not a trivial problem to solve anywhere.
Exactly. And we treat search slightly different from pagination, like naive pagination as well. Like, and there's really no like perfect solution to it. I feel like when you think about like pagination, you could theoretically get a page. Like say you're going to a DB with a limit of 100, you could get a page of 99 things and one thing that you don't have access to. And you got to filter that out and go back to the DB if you really want to fill your page. There's no perfect solution to that in the worst case that we've found, aside from just to filter it out and either make it clear to clients that they might get an incomplete page or have to go back to the database and try to get another page.
Yeah, and the problem gets worse because before you do the query, you don't know how many of those 100 results the user will have access to. So it's, you might do the query and you might say, hey, they have access to 20 out of 100. Okay, I might need to do 5 more of these. But you have to kind of like constantly be re-estimating. And it's very hard if you're trying to provide a predictable latency experience, which I guess you are.
Yeah, there's like 2 strategies that we found are somewhat helpful to mitigate the worst case. The first is to kind of determine like probabilistically how often you get something you don't have access to in your page. And most of the time for us, this is very not often. So, if someone comes to you with, a page size of 100, you could just request maybe like 102 items, and occasionally they don't have access to one of them, but you've still filled the page like 99.9% of the time, and it only becomes a tail issue then. The other kind of trick that we apply more broadly, I wouldn't say necessarily a trick, but it's just like a design principle, is that for these kind of paginated views, we try to define a permission somewhere of the concept of, can you load this paginated view at all, which is not 100% accurate, but is a good enough proxy for whether you should be able to see all the things in the collection or not. And
right. So
yeah, that way you kind of naturally prevent someone who has access to nothing or a very small percentage of the items from even getting to the paginated view.
Yeah. You're on the one hand, you're playing with the numbers game with the, hey, it's very unlikely that you're searching for something you don't have access in the specific Airbnb case. That's because of I guess, like the nature of the business, right? You probably usually have access to most things, especially if you're in a particular view. So that kind of like helps, and then like you narrow things down with that higher level permission first.
Exactly.
We've been talking about latency. We've been talking about like views and presentations. Airbnb again is a big consumer app, a big site. Do you do anything with permissions in terms of like rendering and with a CDN layer, front ends, and mobile? Is there anything happening there?
Not on the CDN layer, from what I'm aware. On the mobile, or I guess more so the front end basis, there's the separate concept of like, can I view this UI component? And the permissions there, we tend to try to draw the line between a data permission and a product permission. And sometimes these are similar, like say I'm able to edit the description for a listing and I'm on the listing management view and I've gotten there successfully, you do want to check that, before rendering the listing description editing component, that I actually have that permission. And you want to check all the components on that view before rendering them. Otherwise, when you try to go and make the mutation, it's going to fail. And those situations are relatively cut and dry. Sometimes we see these sometimes more ambiguous situations where someone's not permitted to see a UI component because it doesn't make sense in the product. But they really are allowed to interact with the data. Like, for example, maybe it doesn't make sense to show someone your host profile when you're in like a specific scenario in the booking flow or something like that. So the product has some kind of logic in the front end that says, hey, don't show this under these circumstances. Maybe it's an experiment, maybe it's a policy for a specific product, even if someone has access to it. And that's what we try to differentiate, where saying, hey, certain kinds of view level or component level permissions aren't actually data permissions. You don't have to manage them in Himeji. You can just write your specific product logic that's really specific to your product, and we don't really care about it because it's not causing any risk of an incorrect user experience or a data leak or anything.
Yeah, that makes sense. And I like the notion of like there are kind of like control and data permissions, right? On the one hand, these are the things that you can do, and the other one is like these are the things that you can see, maybe. Mm-hmm. And this is a typical distinction when you're building a UI, right? There's the kind of like the list of things that you have access to, and then also the list of actions that you can perform. You want to build the UI considering the actions, but at the same time, okay, on the back end, you still have to verify that those things can happen.
Exactly.
Yeah. How did you kind of like validate what you were building with other teams? And we kind of like touched on that. You said, hey, we did some research and we looked at like the time-based cases. We looked at like, hey, we need to go all in. What was that journey like to say, hey, we have this idea, is this the right fit, before you actually built it?
Actually, validating this before started building it was very tricky because it's so much work to implement something like Zanzibar. It's really hard to build a proof of concept. We just had to kind of look at all the existing authorization scenarios, look at what Zanzibar could do with its flexible relationships and its configuration language, and basically come to the conclusion that all of it was possible to be modeled by Zanzibar, and it would theoretically perform well. That was kind of a big leap of faith that we had to take before, diving into implementing Zanzibar over the course of like 3 to 6 months in its like most MVP form. From there, once it was built, the challenge was, like you said, actually moving some of the existing authorization scenarios onto Himeji via writing the configuration, ingesting the data, and starting to add those checks into the data layer. And the tricky part there was just making sure that we had the right authorization rules. In certain cases, the authorization rules were really well defined and well known, because the teams that owned the data and the entities had done a really good job of centralizing that knowledge and that logic. And we just had to do basically a side-by-side comparison running Himeji against the existing logic. And that was straightforward to roll out. In some other cases, it was incredibly difficult to roll out because, maybe in one case, the data was, owned by multiple teams and no one knew the comprehensive set of authorization rules for that piece of data. It was kind of built up across many systems inconsistently over time. And we basically had to do a lot of code reading and reverse engineering, running basically permissions checks in shadow mode and seeing when they failed and trying to dive into each failure and seeing if it was intended or not. And doing that chasing took a lot of time.
Yeah, especially if you had a lot of logic already built, but fortunately, again, like that, one of the benefits of doing that kind of like shadow write, shadow read, and then assess is very interesting. But to prevent customer failures, right? It takes a while, but it's a very reliable way of making those changes. One of the things that's in the blog post, and we touched on, is like there's a UI tool for debugging and one-off tasks. I'm wondering, do teams have access to like the entire set of tuples, or is there a way to kind of like grant some engineers temporary access to a few namespaces, kind of like an FGA, Himeji into Himeji thing, where an engineer might have access to a subset of namespaces, things like that?
We don't have any such controls. All of our namespace configurations are checked in as code. So anyone can go ahead and read the rules as long as they have access to the code base. And for the tuples that are actually stored, those are also pretty much accessible to anyone with data level access. And this is maybe more about the access model for engineers at Airbnb, but it's not that granular. So I could see a need for it, but not necessarily for us yet.
Yeah, that makes sense. No, we've been thinking about some of those use cases, especially like if you think about kind of like building share widgets in the front end directly, where you might be able to accept a token that a user has in their browser. And if you trust whoever signed that token, then you can say, hey, can this user read tuples for a specific object, or can they do things on a specific namespace? So we're starting to explore that like meta FGA into FGA, and we're working on a POC, and I was wondering if you guys had something like that.
We don't have that on like an engineer basis. There's not really a need to restrict access to our internal engineers, but we do have some similar concepts on like a service basis. For example, for a particular namespace, the ability to mutate the actual authorization logic is limited to a specific set of individuals. The ability to actually write tuples about a specific namespace is limited to a specific set of service or user identities. And that's something we declare and allow controlling for in the configuration.
Okay, so that's a config level setting, but it's not something that you necessarily store within Himeji because, well, we mentioned this earlier, like you don't have that many namespaces, but they are fairly complex.
Yeah, and we don't have a need for super granular controls, but it's certainly possible to have super granular controls.
Yeah, that makes sense. What are the latency numbers that you both like look for and see with the system, and are there any pathological cases that you're still figuring out?
Yeah, we mainly aim to be compatible with being parallel with the data layer. So that means that our median latency needs to approximately match our client's database median latency. Our P99 needs to approximately match our client's database P99 so that they can run a Himeji check and fetch from the database in parallel and not have any impact on the total request latency. So in practice for us, that means we target a median of about 3 milliseconds and a P99 of between 15 and 30 milliseconds. And that we've been able to achieve pretty consistently, especially for the cases where we are integrated at the data layer. Where we see pathological cases arise is mostly with regards to nested groups. Sometimes, and this doesn't happen too often at the data layer, but sometimes UI components, the rules for rendering them, and basically product level permissions will sometimes just issue queries that are incredibly expensive to compute. And that's where we need to continue to refine the basically our equivalent of a leopard indexer to bring down latencies in those edge cases. That's probably where latencies get the worst for us. The other case where it can get bad is when we see really poor traffic patterns from end users or internal systems. For example, if if the listings ecosystem is requesting the same set of 1 million listings for days, and then suddenly decides to request a completely different set of listings, they're going to be hitting a completely cold cache, and they're going to see some temporary degradation.
Yeah, that makes sense. Yeah, the cold cache problem is a usual thing, but again, it's not a normal use case, right?
Yeah.
So you mentioned the latency numbers. What are what's the RPS? So it's one thing to do that, I know it's a fairly large number, right? It's one thing to do that I get 100 RPS or 10 RPS, and another thing is like, hey, if you're processing thousands of requests per second.
Yeah, I'll just look off to the side right now. I mean, we're handling on a batch basis, we're handling about 500,000 requests per second in batches of on average 3. So about checking about 1.5 million entities every second at this point. So we're not maybe like 10 times below Google scale for when they publish their paper, but we're kind of getting there.
Well, yeah, an order of magnitude is not that much. You can just say one order of magnitude.
Yeah, really, it's within just an order of magnitude, and that's kind of that latency requirement is actually a huge motivation for how we design the system as well, because you can do things pretty differently at like 100 QPS versus 500,000 QPS.
Yeah, that makes sense, and that's one thing that in this type of systems skews a lot of your design, because there are things that you just can't do for the sake of latency, and that's of course a very big trade-off. But it's what pays off to make that seamless, right? You're essentially handing authorization of the data layer for everyone. You need to make that fast.
Yep.
To close things, and again, this has been a great chat. What are the key things that you learn? Maybe one or two that you say, hey, like these things I hadn't thought of before, or these are the things that I take away from this whole Himeji and authorization at AirBnB experience, not just necessarily Himeji.
Oh, wow. Key learnings, there's maybe several. There were, in terms of what surprised us the most, I think the first thing is how much of a benefit we got from really tailoring our, just the implementation details to the authorization model. Like, I think I've kind of mentioned a few cases in this talk where we really tailored how we optimized to meet how we observe the authorization model to be. And the amount of latency and performance gain that we've been able to achieve from that has been really tremendous. And having super good latency and performance really means you can toss the system just like everywhere. And that makes security super easy. So that was one thing that we learned that was really interesting. When you're reading Zanzibar paper, it seems like kind of a generic system, but as you tune it, it can become, like way more powerful as you kind of like mix Zanzibar and really integrate it tightly with where your authorization model can go.
Yeah, that makes sense.
Another interesting thing that we learned is that this might seem really obvious, but it's actually really important before going down this path that you really deeply understand what the authorization model is. And we knew what some of the authorization model was for certain entities, and for some other entities we didn't know, and neither did anyone else know what the authorization model was. And in those cases, that's when we hit the most challenges, because you're kind of trying to fit the authorization model into any existing optimizations you made, into how you've already tried to define and style your namespace configurations and so on. And after making that mistake one or two times, we now always take the approach of like 100% documenting the existing authorization model really thoroughly before trying to make any new adoption. But in retrospect, I think if we had known all of the, I mean, it wouldn't have been possible, but if we had known all of the authorization models at Airbnb, it would have just made the entire process faster by probably like an entire year.
Yeah, that's something that that's a great takeaway, and something that at least you are seeing again with all of those internal clients. I see that a lot as well with the team at Auth0 Labs when we talk to customers and prospects. The first thing is actually being able to express your authorization model in plain English or any native language that someone might speak. And that's like people are tend to use roles, and they might say, "Oh, it's always been like this," but like what you want and how it should be are usually different from how it is, and in some cases you might even not know.
Exactly. It really surprised us how little, just product owners or, data owners knew of their own authorization model in their ability to express it. They just didn't know how it actually worked or how it should have worked.
Yeah, and on top of that, you need to add that the paradigm shift around like relationship-based access control away from role-based and all of those things that also make it a bit more complex.
Yeah, role-based access control is like the great cancer of access control because it just works kind of great until it completely falls apart super fast.
Yeah, it has some, again, like it's one of those things that you can use. And again, we use it a lot for a lot of things. But when you kind of like get to the edges, either like from scale perspective or from a like dynamicism perspective, it starts to fall off. Yeah.
Yeah, it's kind of a trap almost.
Yeah. Okay, man. Again, I really appreciate your time. This has been a great chat. We'll be publishing the recording soon to YouTube and making it available for anyone that might have missed the part or a lot of people in kind of like our social media audience. But I really appreciate it, Alan, and it was great to speak with you.
Yeah, thank you so much for the opportunity.
Yeah, thank you. Have a good one.
Yeah,
Bye, everyone.
Bye-bye.